Hi everyone, and welcome to the Data Scientist Workbench by IBM, and this is a dimension reduction notebook that I have created, and it includes both the EFA and the PCA. So in this particular lesson, I'm going to focus on the EFA. But before we begin, it is nice to recap what EFA is actually going to be doing. And in comparison to PCA, it is going to be looking at the shared variance between different dimensions. It is going to be extracting the higher order factor that is going to be causing individuals' responses on the scale. EFA is very often not just an exploratory technique, but you should have some sort of hypotheses about the factor solution, and very often individuals who run EFA do have those hypotheses. So EFA is very common in survey research, including some customer satisfaction survey or other personality measurements. Here the individuals might not have the insight or might report about their personality, or they might report under some sort of subjective feelings, which is imbued with measurements error, the heuristics that individuals have, and the biases. So once again, to give you an example, we all know of the higher dimension of personality, extroversion. Some people tend to be more outgoing, some people tend to be more sociable than others. So extroversion in here is a higher order construct, and we do not necessarily have a way of measuring this construct accurately using just one item. So for example, if you're thinking about the books, you can describe the book size using the dimensions of the book, and those are going to be very objective measures. When it comes to extroversion, the construct is a little bit more fuzzy, so we need to think about the behaviors that an individual will exhibit that will indicate that this individual might be extroverted. So we can measure how outgoing they are, how sociable they are, how dynamic they are, and what we will be saying is that all of those variables are going to be sharing some proportion of variance, and this shared variance is actually going to be the factor of extroversion. That causes an individual to be more outgoing, it causes an individual to be more sociable, and it causes the individual to be more dynamic in their nonverbal behavior. Naturally, because individuals are going to be responding to survey items, we would want to account for some measurement error. So in this particular case, it also might be relevant to include some observers who are looking at the person and reporting on the same items to make sure that the observer and an individual tend to agree with each other when it comes to describing someone's extroversion. So factor analysis allows us to identify this latent construct of extroversion and perhaps other personality factors such as openness to experience or maybe how neurotic an individual is. So how to do this? So we're going to be looking at the professor's data once again and essentially looking at the students' evaluations and seeing how those evaluations cluster together. So in here, I'm using the same exact code for PCA, except that I'm creating a new object that's called factor data. And this is just used for the convenience to separate the exploratory factor analysis lecture from the principal components analysis lecture. So in here, once again, I'm going to take a look at the entire data set. There's ID, professor name, the student evaluation dimensions, the presentation skills, explanation, communication, teaching, the workload for the course and difficulty for the course, the student's learning experience, whether they would take the course again now that they know all of the information about the course, and the two subscales from influence and kindness that describe charisma. And those subscales I have created in my own research. So we're going to be focusing primarily on the 6 variables from present to difficulty. So present is indexed at 3 and difficulty is indexed at 8. So I'm extracting the columns from 3 to 8 from our original data and placing this new data table into the object factor data. So I want to make sure now that I have extracted the correct data, and I'm going for the names function on this new object factor data, and I see that we have present, explain, communicate, teach, workload, and difficulty extracted quite successfully, and the object does not contain the other variables that are less relevant, so the ID, professor name, influence or kindness, learning experience, and retake rate. So now we want to decide on the number of factors to extract, and just like in PCA, we're going to be using exactly the same rules. So the rules, the Kaiser-Gottman rule, the variance explain rule and the scree plot rules, they all apply both to EFA and the PCA. So in here, instead of running the PCA, I'm going to extract the eigenvalues from the correlation matrix. So the command core is going to create the correlation matrix from the factor data, and eigen is going to extract the eigenvalues for each one of the components. So here we'll have the eigenvalues themselves, or the proportion of variance in the matrix that each component is explaining. So here we're not relying on any type of rotation just yet. Rotations will come in a little bit later once we start developing our theories and hypotheses, but we're simply looking at how much variance in the matrix each component is going to be describing. So this information is exactly the same as that we had in the PCA. So essentially, the first step for the EFA a lot of times is to conduct the PCA. So you can see the first component is explained 3.440 of the variance measures, and the second component is 1.96. So using the Kaiser-Gutmann rule, we can cut it off right here to two components, because the first component through sixth component do not explain more variance than would be explained by any single dimension on its own. Here we have the factor loadings, so those are very similar to the ones that we observed in PCA. So the items present, communicate, teach, and explain all loads on factor 1, so perhaps describing professor's social skills, and workloads and difficulty are loading on the second factor, so perhaps describing the course difficulty more so. So now we're going to generate the scree plot using these data right here. So we're going to be plotting these numbers on the y-axis and each component on the x-axis. So what we see in here is that the first component and the second component explain a substantial amount of variance, and after the third when it comes to third component through sixth component, they're not explaining any additional amount of variance, and hence we will be drawing an imaginary line in here and retaining only the two components for our factor analysis. So we can also take a look at the proportion of the total variance that is explained. So we'll be using the eigenvalues once again from the object eigenvalues that we have generated, and dividing it by the sum of all eigenvalues. So the sum of all eigenvalues is going to be essentially how much variance there is in the matrix, and we'll see how much each one of the components explaining the proportion of variance that each one of the components is going to be explaining from the total amount of variance. And we can see that first component is explaining about 57% of the variance, second component is about 28% of the variance, and the third component is going to be explaining only about 7% of the variance. So you can see once again that the variance explained, the cumulative, the variance explained by the components from 3 to 6 is much lower than by the components 1 and 2. So we'll probably want to retain the two components once again. Adding up the first two components, we can see that we can explain about 85% of the total variance in the matrix by just relying on the first two components. That's pretty cool. So what kind of rotations are we going to use? If you think back about the code book that I have described in the PCA lecture, what we see immediately is that the students' evaluations are partitioned into 4 variables that describe professor's social and communication skills, and 2 variables that describe the course difficulty. So it is very unlikely that communication skills are going to be highly correlated with the course difficulty measures. So we can assume that those two are probably not, the 2 factors are probably not going to be related to each other. So we're going to be using the orthogonal rotation and the variomax rotation in particular to maximize the variance that each component is explaining, and the loadings on each one of the factors, but at the same time increasing the distance between the 2 factors, so not modeling the correlation between the factors. A new concept would be the factoring methods, and automatically R is going to be executing the maximum likelihood factoring, but here we will use the regression-based principal axis factoring because it is most common method in psychology research and much of the research in general. So principal axis factoring essentially says to place the factor communalities in the diagonal. So you're basically accounting for the measurement error, and you're looking how much of the variance in each item is explained by the factor structure. So we have two factors, and how much of the variance in each item is explained by this structure. And we will estimate also the residual variation and state that the factors do not explain all of the variance, and there's some leftover variance altogether. In PCA, in comparison, the ones are retained across the diagonal. So that is suggesting that we measured the variables without error. So let's recap the pre-processing steps and decisions that we have made. So we have extracted the data. We have the number of factors that we've decided to be 2 from the Kaiser-Gottman rule, the scree plot rule, and examining the cumulative variance explained. We're going to be using orthogonal rotation and the factoring method. So as you can see, there's more variables that we need to consider, more decisions that we need to make when we're performing factor analysis, and a lot of it is going to be determined by your question. So factor analysis is often approached from the top-down sort of view, but it is not necessarily so. You can perform factor analysis bottom-up and be completely data-driven, but usually people have some sort of sense about the factors that are going to be emerging. So to run EFA, it actually is going to be quite easily. First, we're going to create the correlation matrix and store it in the object format. And once again, we see high correlations between all of the communication items, high correlations between difficulty and workload, and low correlations between the two factors, suggesting that the factors probably are, in fact, orthogonal. So now we're going to be creating the EFA solution object, which will contain all of the information from this function FA, which stands for factor analysis. We're going to give the factor analysis function the correlation matrix, specify that we want to extract two factors. We're going to rotate the factors using the varimax rotation, and we're going to be using the principal axis factoring methods right here. FM equals principal axis factoring. And to view the solution, we're simply going to type EFA solution, so the name of the object itself. And right here you immediately will see your loadings for each factor. So principal axis 1 contains the items present, explain, communicate, and teach. And here you can see that the loadings are quite high. And the loadings are much higher in here than in PCAs because we are considering only two factors, but also because we're maximizing we're trying to subsume all of the dimensions within the single factor. So due to rotation, we're going to be moving our axes to ensure that lower order dimensions actually fall on the principal axis 1 or principal axis 2. Typically, individuals in the survey research will use a cutoff of 0.7 to actually retain the item on the factor, and as you can see in here, all of the items are loading quite well at the principal axis 1, and all of them are above 0.7. Same can be said about the principal axis 2, so the factor 2. The loadings are quite high. If you're more liberal, you can go for 50, 0.50 cutoff, and some people go even as low as 0.40. So now here we have the rotated factor solution for the two factors, and these sum of square loadings are essentially going to be your eigenvalues. So as you can see, they're fairly consistent what we have obtained with when we just did principal components analysis or extracted the eigenvalues themselves. So here is the proportion of variance that is explained, and cumulative proportion of variance. So here we're explaining in total about 77% of the variance in our correlation matrix. Finally, we have some fit measures in here and a test of the hypothesis that two factors are sufficient. And all of these data are, especially the root mean square error of the residual is going to be 0.03, which is relatively low, suggesting that two factors are probably a pretty good solution that we have more general. So to evaluate the solution itself, so we're looking at the model that we have specified in here, and that's the objective function was 0.39. Objective function itself is going to be distributed as the chi-square. And here we're just going to extract the p-value for the chi-square for 0.39 and for degrees of freedom, and it's 0.98, suggesting that we have a fairly good fit. So our factor structure, of two factors, and with all of the loadings included for each factor, is explaining the data variation in the data quite well. So we can graph this using the fa.diagram EFA solution, and what we'll get is the principal axis 1. That is going to our new factor, principal axis 1 and principal axis 2, and they're causing their respective items. So factor loadings are going to be displayed right here. So typically we mark the factors with circles and observed variables with squares. So that is what we're saying is that this principal axis 1 factor, which we'll be calling social skills later on, so we're giving it a name already, is going to be causing individuals to perform quite well in their explanation, teaching, presentation, and communication. And the principal axis 2, the course difficulty, is going to be causing individuals to evaluate the courses as more difficult and that the courses have greater workloads. So factor 1 causes variables explain, teach, present, and communicate, and factor 2 causes variables workloads and difficulty. Naturally, you might want to name your factors to ease interpretation and just sort of enjoy this process.